Thanks for the introduction. Hey guys, it's a pleasure to be here. Awesome, yeah. Let me tell you some story from the trenches that we are fighting, where we are fighting every day. This is joint work with Vova Kuznetsov, Laszlo Shekaris, George Kandea, R. Shekhar, and Don Song. Most of the work has been done at UC Berkeley. Vova and Laszlo did most of the heavy programming work and heavy lifting, while I only coded some of the support libraries and a little bit of some of the other stuff. But most of the programming praise goes to the two students. Also, blame me for all the bad jokes in the presentations. It's not their fault. So let's start right away. We live on an ugly planet, a bug planet, and it's just terrible out there. There are so many bugs, it's just crazy, and we are overrun by them. If we just look at what happened in the last couple of years, for example, pointers not working. Memory corruption bugs are abundant. They are everywhere. They are just literally everywhere, and there are so many CVEs out there that where an attacker can gain some form of control flow hijack permissions or capabilities. And this is just we just picked a couple of programs out there, like Acrobat, Firefox, IE, General OS X, and Linux bugs that allow an outside attacker to gain control flow or code execution capabilities on a system. And the attacks are on a rise, and all of these attacks rely on some fundamental memory corruption vulnerability somewhere in the background. And we are being overrun by all these bugs. Even though we are investing more and more time into fuzzing and tools that find bugs, there are just way too many out there that we can fix manually. So we have to come up with some techniques that allow us to have some proactive steps against these bugs and vulnerabilities that are in our software to protect them against different form of control flow hijack attacks. And just to name two prominent examples this year, there was the Heartbleed vulnerability, which was a memory safety or a memory corruption vulnerability, and shell shock as well. And some of these vulnerabilities, they sleep and slumber in the software for many and many years. And suddenly they are found and they can be exploited on a very, very wide scale. And I argue that we have to come up with some proactive defense mechanism that protects us against these kinds of vulnerabilities. So let me take a step back and explain you what memory safety is all about and why we don't have it yet. So at the most basic level, memory safety relies on some form of, or memory safety corruption or lack thereof, relies on some form of invalid dereference. So for example, there can be dangling pointers. It could be a temporal issue. So for example, at one point in time, in a language like C or C++, we have a memory object, and we have a pointer to that memory object. So we have a valid reference. But we free that object at one point in time, and it becomes an invalid object, and there's a dangling pointer to that object, which can lead to some form of memory corruption when we dereference it. Or they are out of bounds pointer. Imagine that we are working and iterating through an array, and as soon as we step outside of the array, we have an out-of-bounds pointer, which is some form of spatial memory safety violation. Both of these pointers are still fine as long as we don't dereference them. But something bad will happen if the pointer is read, written, or freed again, and we end up with some form of corruption. So otherwise, there's no violation. The threat model that we're going to have for this talk looks as follows. We assume that our attacker can read and write arbitrary data in the whole process image. The attacker can read code as well, but the attacker cannot modify the code as it is being executed. And we'll discuss some of these limitations later on. Or the attacker cannot influence program loading. So if the attacker has control of the whole process image before we can actually set up our defense mechanism, there's nothing we can do. So to speak a little bit more permission-wise, there are Rx permissions for the attacker on the code, but the attacker cannot change the code pointers. There's read and write for the heap and read and write for the stack. So just so that we are all on the same page, I'll quickly walk you through some form of control flow hijack attack as it is being used nowadays to sidestep all the defense mechanisms that are active on current systems, so that we can understand how the defense mechanisms that I'll present later on will work. So we have this simple C program. On the left-hand side, we define a function pointer, and there's some weird pointer arithmetic going on where we assign Q to a buffer plus some attacker-controlled input. So the attacker can kind of point Q somewhere into memory by carefully crafting the input to that pointer. After that happened, the function pointer is assigned to the function foo, but later on, the attacker-controlled pointer Q is assigned a value. So initially, the programmer intended Q to point into the buffer, but the attacker can overwrite or can control Q to point to some function pointer later on somewhere in memory. And as a second step of the attacker can write to that function pointer, and instead of pointing to the valid function that we want to execute, the function pointer now points to an attacker-controlled gadget, and this allows a control flow hijack attack that the attacker can then exploit as soon as the pointer is dereferenced. And as soon as that happens, all the bets are off. The attacker runs code and can get control over your system. But you might say, we've got all these fancy defense mechanisms out there. What about these existing defenses? So yeah, that's actually true. We've got a bunch of defense mechanisms, like data execution prevention, which prohibit an attacker from injecting code. That's why I assumed in the beginning that the attacker cannot modify the ongoing code. So this is all fair and nice. But in addition to that, a problem on current systems is that the attacker can restitch individual gadgets right next to each other and thereby execute arbitrary code, so-called return-oriented programming or jump-oriented programming, if you want to look it up. There's ASLR, which is a nice probabilistic defense mechanism that shuffles memory around, but it's only a probabilistic defense. And if we assume that the attacker can read arbitrary memory, the attacker can easily sidestep this defense mechanism by reading out some pointers and thereby reconstructing the randomization algorithm that was used and thereby leak the correct addresses and craft an attack carefully that sidesteps this defense mechanism. And the same goes for stack canaries that protect against overriding the return instruction pointer on the stack. If the attacker can read out the stack frame before that, the attacker can carefully craft an attack that sidesteps this defense mechanism. So it looks like we're a host, right? If you want to know more, there are a bunch of nice papers out there, or you can just watch the talk from last year, where we evaluated all the different kinds of war games that are in memory and how these war games all play together and how an attacker can exploit them. So now that we know that we cannot just use C code or C++ code because the code is full of bugs, you might say, haha, memory safety to the rescue. We'll just move to a safe language, right? Instead of coding in C or C++. Program language research has come up with a whole bunch of languages. There's Python, there's Java, there's C#, or there's Swift. These are all memory-safe languages, and these problems that I just talked about would completely go away. Sounds good, right? So where do we stand? Let's look at the Dropbox uploader for your files. It's written in 3K, 3,000 lines of Python code. Completely memory safe. Everything is good, right? There's no way you can exploit that code. But imagine, to run these 3,000 lines of Python code, what do you need on top of that? Well, for one, there's the Python runtime. 500,000 lines of code. It's written in C. And again, we have all the memory corruption vulnerabilities. In addition to that, we use the libc to do all the codes, to do all the system calls. 2.5 million lines of C code. And on top of that, there's that thing called the Linux kernel, or the Windows kernel. Another 16 million lines of C code. So C code or C++ code, low-level languages are not going to get away. There's no way we can fix all these bugs. And it's just way too much of an attack surface. And we need to come up with strong defense mechanisms for those. So if you look at the current state of defense mechanisms, a lot of the code that runs on the system, even if you program in a safe language, is actually unsafe. And only a small, tiny little subset is written in safe code, if at all. So if we compare how close are we to safe languages, we are way off. And there's a huge way to go. And we need to get much better. So you might say, okay, fair enough. We cannot rewrite everything in a safe language. So let's just retrofit safe language on top of the old languages, right? Sounds like a good idea, because memory safety first. All these bugs would go away. And academia and industry came up with a bunch of defense mechanisms on top of that. So you can just plug into your compiler and more or less easily just recompile your software, do a couple of 100 hours of code changes, and you're good to go. So there's softbound plus CTS, which is a great defense mechanism that retrofits memory safety on top of C and C++. But it comes with a almost 120% price tag. So it's fairly expensive. Also, it's not exactly compatible with all the code. But it runs most of the code, or a lot of the code. There's Ccured, that tries to retrofit memory safety on top of the C language and restricts or enforces a stronger type system that then comes with some form of memory safety on top of it. But again, it comes with a 60% price tag, which is way too expensive in practice. Or there's Address Sanitizer, which is great for debugging and a great tool. But it's, on one hand, it's only probabilistic, and again, it adds 73% overhead. So even though we know that as the tools are right now, they have way too much overhead, that's what we want to do. We want to retrofit memory safety on top of these existing compilers and then enforce it at runtime to ensure that we are protected at all times. And just to show you where this overhead comes from, I'm going to give you an example of how Softbound would enforce memory safety on this small program. So we've got a couple of lines of C code. We have a buffer that is allocated. We have our pointer Q again, which is from the motivating example, which is assigned the initial base address of the buffer plus some user-controlled input. Softbound is a compiler-based transformation that adds additional checks in the background that are then executed at runtime. So first of all, it assigns metadata to all the pointers. So as soon as we declare buffer, there are two additional variables declared that contain the lower and upper bounds of the buffer itself. So we have a lower pointer and an upper pointer, and those are carried along all the axes and so on. If we do have assignments from other types or across pointers, we propagate metadata. So we see that QLow, the two variables QLow and QUpper, are assigned the lower bounds of the buffer and the upper bounds of the buffer. So this metadata is carried along and can be used for further protection. In addition to that, we have a dereference or a check whenever that pointer is used. So before star Q equals input 2 is actually executed, we do a check if the current value of Q is inside the bounds and abort otherwise, which protects us from any possible attacks against that would assign it out of bounds. So the function pointer cannot be overwritten in this example. So what we have is, or what we get is these 116% performance overhead, because there are just way too many pointer assignments in low-level languages like C or C++. And the compiler has a very hard time at optimizing these and getting rid of all the surplus assignments. So in reality, or with a perfect compiler, we should be able to prove for many more accesses that they are actually safe. But it's very hard to reason about these things on the compiler level. And therefore, we have this very high or fairly high overhead, even with a very sophisticated compiler analysis framework like LLVM offers. So it looks like this, right? We are walking towards that safe haven. And we do have that safe haven. But we are facing a problem that we either have safety or flexibility and performance. So it's an either or, which is really, really bad. Ideally, we want to have both safety, flexibility, and performance. You might want to know more about memory safety. Feel free to either read the paper or watch last year's talk by Andreas, who presented Softbound for FreeBSD. So now that we know how memory safety works, can we adapt it somehow so that we can protect only a small set of data? We no longer want to protect all the data, because that's way too expensive, right? Otherwise, we would run again into this high overhead. But possibly, instead of protecting all the data that is out there, let us just focus on a small subset of data and protect that small subset of data. So just a couple of code pointers on the heap and a couple of pointers and variables on a stack that we deem to be protection worthy. So instead of just enforcing a probabilistic defense for all the data or a strong defense mechanism for all the data with high overhead, we offer strong protection for a select subset of data. And in addition to that, we have a very different attacker model to other defense mechanisms. We assume that the attacker may modify any unprotected data that is out there. And the attacker can freely write to any of the data that we don't really care about. So instead of protecting everything a little, we protect a small set of data completely. And just to give you a peek preview, we change the overhead numbers from complete memory safety, which faces 120% overhead, to as low as only 2 to 8% overhead if we protect only code pointers. So we focus for our protection on code pointers and enforce strong memory safety for code pointers. So anything that is used in a control flow decision at one point in time, through an indirect jump, through an indirect call, or anything like that, will be protected by our defense mechanism. But we don't care about any of the data that is on the heap or on the stack, and we focus only on the small subset of code pointers that actually are used for control flow decisions. And therefore, we can protect against control flow hijack attacks. We don't protect against any data attacks, though. To actually enforce this, we had to come up with a set of special techniques that transform your program into a protected program. One of the core ideas that we have is something that's been out there or has been used in networking for decades, but hasn't been used in software engineering. We separate control data and the control plane and the data plane. So instead of having just one single view of memory, we separate the program memory into two different views. So on one hand, we have the regular memory with all the buffers, all the pointers, and so on. And on the other hand, we have safe memory. And our safe memory contains code pointers and code pointers only. The regular memory, on the other hand, contains all other data. So that looks quite bad, right? But I guess you get the gist. So safe memory contains all the safe code pointers. Regular memory contains everything else. Just that memory locations for the function pointers are not used. The memory layout itself is unchanged. So in the place where a code pointer was before, there will just be an unused block. In the control plane, any memory location is either a code pointer or null. And we can impose this memory view using some compiler-based technique. And enforce that the safe memory region only contains code pointers and nothing else using the transformation. But more on that, that later. So for now, just remember that we split the memory view. We have a safe memory view that contains code pointers, nothing else, or null values, and the regular memory with the rest of the data. So on the stack, we have a different kind of technique. We split the stack similar to the heap memory into a safe stack and a regular stack. Has it been like this since the beginning? There's like a third of the slide cut off. Let me try to do something. That's annoying. Yeah. So much for TVI out. Okay, let's try to continue. So we've got the safe stack and the regular stack. On the safe stack, we add an additional compiler instrumentation pass that looks at all the local variables on the stack frame. And everything that we can prove in our instrumentation path that is safely accessed, so any local variable that is safe, is pushed to the safe stack. While all the other variables that we cannot prove are safe are pushed to the regular stack. So stuff that could cause something to be unsafe is either some weird pointer arithmetic, if it escapes the local. What the heck is this? So if it escapes the local stack frame, or yeah, whatever, we push it or we keep it on the regular stack. And we assume that the attacker can corrupt anything on the regular stack. So we ensure complete safety on the safe stack. We don't give any guarantees on the regular stack. So if you look at our small code snippet, the variable R and the return address would be pushed onto the safe stack, and the buffer would be pushed onto the unsafe stack, and the attacker could corrupt some of the other stuff on the unsafe stack. So in using this principle, we can ensure that the attacker can only corrupt data that we're not interested in protecting. And we can decide how much of the data that we want to protect. And in our case, we protect anything that's code pointers, that contains code pointers or is used in control flow decisions, or can be proven or is proven to be safe on the stack frame. So if we look from above at the memory layout, we have two areas of memory. We have safe memory for code pointers and regular memory for all the other pointers. For the safe memory, we ensure and guarantee that all the accesses are safe. While for the regular memory, they are fast, but we don't give any other guarantees. In between safe memory and regular memory, we use hardware-based instruction-level isolation, using some technique like segmentation or some other form of blinding. The regular memory contains regular heap, stack frames, and the read-only code regions, and the safe memory contains likewise the safe heap, the safe stack, and the safe stacks of the individual threads. So now that I've shown the basic overview of how we separate code pointers, and it's actually just like in the name, code pointer separation. All the code pointers are in a completely different memory space. How much protection does that give us? Let's look at how we can attack code pointer separation. We have this small C program here. It looks very similar to the motivating example I used in the beginning, with a slight difference. So instead of just assigning a function pointer, we assign a function pointer through a struct. So let's assume that the function pointer is somewhere in the struct, and we have a doubly indirect dereference to the function pointer. Again, we have the opportunity for the attacker to corrupt the buffer, and we know that the attacker cannot corrupt the function pointer itself, because this function pointer is in a completely different memory space and therefore protected. So the attacker, using this simple write, which has a different type, and our type-based analysis ensures that the function pointer is in the other memory space, the attacker cannot overwrite the function pointer itself. But what the attacker can do, the attacker can overwrite the struct pointer and let it point to somewhere else in memory, where possibly there might be some other function pointer lying around. So if you assume that this, or if you think back to that different memory view, that code pointer memory view contains only code pointers, or null. And whenever a region is freed, we clear the code pointers in addition to that. So this memory view only contains the code pointers that are currently active and in use. But using this kind of technique, the attacker can redirect it to some other code pointer, which is a null or a pointer to another function. But we'll see what the defense mechanism in the end is like. So using the compiler-based technique, in our analysis phase, we identify all code pointer accesses through some static type-based analysis and redirect them to the different memory view. The two memory views, again, are separated using instruction-level isolation, for example, segmentation on x86 or blinding on x64. And we give a bunch of security guarantees. So using this separation, and you have to think about it for a while until you understand the security guarantees. This separation ensures that the attacker cannot forge any new code pointers. So using a memory write, using a non-code pointer type, the attacker can never write to that safe memory view. We guarantee that any pointer that is written into that safe memory view is either an immediate, like a fixed value, or assigned from another code pointer. Therefore, an attacker can never construct a code pointer to some other location in memory. What the attacker can do using that doubly indirect or going through multiple indirection, can replace existing functions through these indirections. So for example, foo bar function can be turned into foo bus function. But it must be a code pointer, it must exist, the current memory region must be valid at that point in time. And then a successful attack is very unlikely for this. So what we basically did is we took all the code pointers that are used in a program, group them together, and make them look out for each other and protect them against other modifications from non-code pointers that are out there, and thereby protect them against other modifications. Also, if you think about it, all the memory safety violations, they are usually not in pointer arithmetic to code pointers, but in pointer arithmetic to some other buffer or some other input. So it is very likely that this will be exploitable. So this is the simple code pointer separation, but can we do better than this? Remember, we talked about memory safety before, and here I didn't talk about memory safety yet. So let me see. Code pointer integrity takes code pointer separation as a baseline, and in addition to that, enforces memory safety for the code pointers. So the sensitive pointers that we protect are the code pointers And in addition to that, any pointers used to access these sensitive pointers. So everything that's used in the dereference chain automatically becomes protected as well. In addition to that, we enforce bounce checks, as I've discussed before, for all the sensitive pointers that we identified. We could identify individual instances of safe sensitive pointers, but we do an over-approximation, which does not lower security, but might increase overhead. Instead of protecting individual instances, we protect types that we identify and deem to be sensitive. So it's an over-approximation, which is safe. This over-approximation only affects performance, but we measured on SPEC 2006, which is a standard benchmark, that using this full transformation, roughly 6.5% of all the memory accesses are accesses to sensitive data. So let's see how our example looks like if we have bounce checks in addition to the separation. Just like in the example of memory safety before, we add the lower and upper bounds, and we execute an additional check if the bounds are still valid. And before the attacker could override the function pointer or redirect the struct pointer, an exception would be triggered whenever that is dereferenced. So if we compare code pointer integrity and code pointer separation, what additional kind of security guarantees do we get? Both defense mechanisms separate sensitive pointers from regular data. Both of them are based on or use a type-based static analysis. But where they differ is what sensitive pointers are. For code pointer separation, sensitive pointers are code pointers only. For code pointer integrity, we add, in addition to that, pointers to sensitive pointers, which is a recursive definition and kind of follows the dereference chains and we therefore protect anything that points to code pointers directly or indirectly through any chain. We guarantee that accessing sensitive pointers is safe. So we use instruction level granularity separation, and for code pointer integrity, in addition, we use runtime bounce checks on top of that. Also, on the other hand, accessing regular data is safe, is fast. So we don't impose any additional instructions when accessing other regular data that we don't want to protect. And this allows us to get very low overhead. So what kind of security guarantees do we have? For code pointer integrity, we offer a formally guaranteed protection. And if you are interested in the more theoretical aspects, we do have a formal proof in our paper. All in all, if we enforce memory safety for the code pointers and the sensitive pointers that we identify on top of it, we run into 8.4 to 10.5% overhead for roughly 6.5% of memory accesses, which is almost deployable, and definitely deployable if you are interested in protecting against specific attacks or in different security contexts. For code pointer separation, we offer strong protection in practice. So it will be very hard for an attacker to find an exploitable condition. We don't say it's impossible, but it will be very hard. It's definitely much stronger than any of the defense mechanisms that exists currently. It offers complete protection against anything that, against any return-oriented programming attacks, and strong separation for anything, any code pointer that is on the heap, at almost negligible overhead. We have 0.5 to 1.9% overhead, so 0.5 for SPEC CPU and 1.9% average overhead for the Phoronix benchmarks. And we protect roughly 2.5% of memory accesses. What we can also do is we can only use the safe stack, which protects the return instruction pointers on the stack. And we offer full protection against return-oriented programming attacks at negligible overhead. So we've got different levels of defense mechanism that you can use whenever or however you feel like, and how big your budget is. So if you want to give strong deterministic guarantees, use code pointer integrity. If you want to protect, if you want to use strong protection, use code pointer separation. If you just want to be sure that the return-oriented programming is not possible, use the safe stack. So enough of the design of the system. Let's talk about the implementation. We implemented it on top of Clang, where we collect type information, and all the transformations are then done on an LLVM instrumentation path that either or does CPI, CPS, and the safe stack. We have additional runtime support for the safe stack and the safe heap and all the management functions on top of that. And currently we support x64 and x86, although x86 is a bit shaky. For the systems, supported systems, we support Mac OS X, FreeBSD, and Linux. The current status of the implementation, this is a research prototype after all, right? So nothing is perfect. We have great support for code pointer integrity, separation, and stack pointers for Mac OS X and FreeBSD on x64, and fairly good support for the other architectures, but we are working on improving the code quality. We are currently in progress of upstreaming the patches. And as you might imagine, there's a whole bunch of changes out there. So we built a couple of chunks that we are upstreaming one after the other. And currently we are working on the safe stack, because that's the logic first choice. It has lower overhead than stack canaries that are currently used. It offers full deterministic protection, and it's widely compatible with anything that's out there. It's easy to add and gives you very strong protection. So this, we're hoping to finish integrating the safe stack soon, and we'll then continue with the CPS and CPI patches. You can fork the current version on GitHub. It's all out there. Feel free to give it a try. And we're happy to hear back from you if you find bugs, if you find other things. Also, we're currently working on a code review for code pointer separation and code pointer integrity. There's still a couple of bugs to be fixed. You can still play with the prototype. It's out there. Download it, try it out. We will definitely release more packages and updated sources soon. And also, we obviously run into some problems as well. And there were some changes to super complex build systems. Like, for example, when we worked on FreeBSD, we had to adapt some of the larger makefiles to actually get it to run. So you might ask, is it practical? Well, it is. So we recompiled the complete FreeBSD user space with our protection. And in addition to that, more than 100 packages with strong protection guarantees, where we can now guarantee that control flow hijack attacks are no longer possible at fairly low overhead that you will run into. So now it's up to you to do your part. Look at the code, try to port some of the more complex makefiles, try to find bugs in our implementation, help us get the word out there, get distributions to actually use these patches, let attacker accessible software be compiled using a very deterministic and strong defense mechanism. And if we compile our software that is reachable, or code that is reachable from the internet using these strong defense mechanisms, we can stop control flow hijack attacks. So let me conclude. Code pointer integrity and code pointer separation offer strong protection against control flow hijack attacks. And the key insight that we had here is that we offer memory safety for code pointers only, which allows us to limit the overhead that we actually incur, bringing down the overhead from almost 120% to less than 2 to 8% on average, for depending on if you either use code pointer separation or code pointer integrity, which is easily deployable in practice and can be used on a very wide scale without impacting the runtime performance of current software. We do have a working prototype which supports unmodified C and C++ at very, very low overhead in practice. Upstreaming of our patches is in progress. The safe stack should be available soon. You can fork it on GitHub. You can read the paper on our homepage. We'll be happy to hear from you if you have questions, if you find bugs, if you want to audit the code or help in any way. And if we continue like that, we'll go on and we'll be able to understand the bugs, and then in the end, we can get rid of them and protect against them. And with that, I would like to close my talk, and I'm happy to answer any questions. Thank you.
Thank you very much, Matthias Plyer. As you heard, he's open to questions now. We have 4 microphones in the room. There's microphone 1, microphone 2, 3, and number 4. You can go up on any of them. I'll just pick them, well, one after another. And I will start with microphone 2, please.
Thank you for a fascinating talk on the obvious approach here. I've just got one question. You've discussed extensively the overhead in runtime. What's the overhead in memory footprint? Because normally the page size will be the limit for your hardware protection.
So the overhead is not too bad. Naively, you would just chat out a memory space, right? What we do, we've got several implementations where we store the code pointers and the metadata. You can use a hash map, a compacted hash map, some form of array or some other data structure that is just protected and moved to the side. I'm not 100% sure if we put numbers into the paper, but they are in the low digits. So there's not too much memory overhead. Because for one, there are only very few code pointers, so we don't need to store an excessive amount of data. Also, we can store them in very compact representations using some form of hash map or something like that, that gives us the illusion of the full memory space. Okay?
All right, thank you. Microphone 1, please.
Yes, in your motivating example, the biggest chunk of potentially vulnerable C code was the Linux kernel. And I was wondering whether this kind of protection is practical in kernel space and with full permissions in hardware.
That's a very good question. It's also a very hard question to answer. So for the C code, we'd be perfectly fine. Unfortunately, the Linux kernel contains a whole bunch of assembly code and inline assembly code, which is very, very hard to protect. So we cannot give any guarantees for inline assembly that is in the source code. We could imagine some form of annotation-based system where the programmer has to identify assembly or inline assembly sequences that modify code pointers. And if so, we could give the same guarantees. But we would, so our instrumentation path runs on top of LLVM. LLVM does not have any type information for the inline assembly code that you put into the code. So if you as a programmer would supply additional annotations so that we could reason about the inline assembly code, we would be fine. But that would be definitely ongoing work. Thank you.
We have a question from the internet.
Yes, thanks. There's still an open question in the chat room. The question is, how are the address spaces separated, the pointers from the code?
Yeah, that's a good question. On x86, we use segmentation, a segmentation register that we set up. So we can easily enforce, easily use hardware-enforced separation. On x64, we can use a set of different techniques depending on how much overhead you're willing to pay. You can use ASLR, so you can use a randomization-based approach, and just use or allocate your safe region somewhere in memory that is safe from the attacker, because in a 64-bit address space, the address space is big enough so that you can hide it. And in addition to that, we guarantee that in unsafe memory or in attacker-accessible memory, there will never be a pointer to our safe memory. Therefore, we are safe against information leaks. Or if you're willing to pay 2 or 3% overhead, you can blind out a memory region. So imagine it that for every memory access that you execute, or every memory read or every memory write that goes to unsafe memory, you do an AND to the actual address that is used, and therefore blind out with a mask, blind out the bits that are the protected memory, which costs you like 2 or 3% overhead.
All right, microphone 2, please.
At the beginning of the talk, you mentioned the Heartbleed bug, and as far as I could tell, none of your security measures would help against it.
Yeah. So the Heartbleed bug is a piece of information that it's basically a data leak, right? So you could protect against the Heartbleed bug by extending the protection that we currently have to other data types as well. So you've seen that we basically run a type-based analysis, and we currently identify everything that's like a code pointer or used like a code pointer or anywhere in the chain when a code pointer is dereferenced. But there's nothing that stops us from adding additional data and increase the protection for that additional data. So instead of just protecting code pointers, we can select other data as well. And sensitive data types like private keys would be very good candidates for additional scrutiny and inclusion into the set of sensitive pointers. So that's definitely ongoing future work.
All right, microphone 3.
All right, you've mentioned that you've evaluated the performance with the spec benchmark. Have you also evaluated the functionality? You've mentioned that you've compiled the FreeBSD, the whole FreeBSD set and a couple of hundred packages, but have you also run them successfully and all?
Yep. So spec CPU is a self-validating benchmark that checks if the code runs correctly and verifies that it runs correctly. And so does Phoronix. So we did run the Phoronix benchmarks on top of FreeBSD, which is a big package of benchmarks that self-verify the results and ensure that they are correct.
And then you've mentioned that you have runtime support. What does that entail, and how portable is that?
So we do need runtime support to set up all the data structures. We need runtime support to set up the safe memory and so on, which is basically like, do you know compiler RT in LLVM? It's like a library that is linked into any or included into any executable that is compiled. It's like GCC has its own library and so on. It just contains a set of startup functions and so on that set up the process image. When you execute a program, it doesn't start at main. There's a whole bunch of other CRUD that is executed beforehand. And we add to that stuff that is executed beforehand. It's a standard compiler technique to include some initialization functions and stuff like that.
All right, thanks.
Thanks.
All right. There's another question from the internet.
Yes, thank you. Another question is, what about applications with runtime code, e.g. browsers? Can you protect these?
Yeah, so that's a good question. At the beginning, in the assumptions, I put in that there's no self-modifying code, basically, and browsers use a lot. basically JIT compilers and therefore recompile code all the time. There are two answers to this question. One of them is if you lift the compiler, the just-in-time compiler itself, into the trusted computing base, and you instrument and give the compiler access to all the support functions, the compiler can produce safe code as well. But the drawback, obviously, is that the compiler itself then is inside the trusted computing base during the time the process or the program is executed, and might be attackable if there are bugs in a compiler, obviously. The other option, or the other answer, is that most of the time, even if we don't give any strong guarantees, the compiler, the just-in-time compilers that we use in browsers, compile a memory-safe language. And inside this memory-safe language, the attacker doesn't have access to code pointers directly. So it should be safe in most cases. But obviously, it's not a perfect answer. That's why we included it in. That's why we excluded JIT compilers or just-in-time generated code from the attack model. You can come up with some defense mechanism, but you'll have to verify the compiler. That's a short answer.
All right, thank you. There's still 3 questions left at microphone 2, I guess. Go ahead.
So you said that this doesn't work in all cases, so it works in almost every case, but it doesn't work for some cases. You already explained that this one wouldn't work for inline assembly and stuff like that. What are the other cases this doesn't work?
Well, not necessarily not work, but for code pointer integrity, there are sometimes very weird casts. Like C code, if you look into what is actually compiled and written out there, then C code becomes very, very ugly. And according to the C language specification, you're allowed to cast everything into void or char. And if you have a bunch of these casts, from code pointers to void and back and forth and all that, you end up protecting all the pointers, and then you end up with a fairly high amount of overhead. So it actually happens a lot that pointers are cast into a char pointer and then back into a struct pointer that then contain a code pointer. And if that happens, you might end up protecting all the pointers, which then results in fairly high overhead. So you do have high overhead as a drawback. What we don't support is if something weird happens from the hardware. So if you would protect the VMM, or if you have access to page tables, let's say in the kernel, if the attacker, we don't protect data memory. So if the attacker writes into the page table or something like that, you could come up with very weird stuff. But in user space, you should be safe.
Hi there. So it looked like from the talk that all of the work here is being done in software. I was wondering, do you see any opportunities for hardware acceleration in, say, the CPU to reduce some of the overhead?
You're talking about MPX?
MPX or anything else you can come up with.
Yeah, we actually looked at MPX. It's a bit of a bummer that it's not available in real hardware yet. But then again, Intel kind of advertises MPX as a debugging feature. There's some hints that it'll have up to 40% overhead. So we'll definitely look into MPX as soon as it is out there in real hardware. What we could really profit from is some faster implementations for the additional tables that we have, like for the bounds information and so on. And Intel tried to address that using MPX. Something following this line of work could be interesting, or some other doubly lined lookup that you can speed up using some additional instructions might be interesting as well. Yeah.
Thank you. Next question.
Hi. I wanted to ask, what is the interaction between this and dynamic linking? For example, what happens, or can you link unsafe plugins that aren't compiled with this blobs into your code and have guarantees or safety, or the other way around, have a user program that's not compiled with this, loading a safe library.
So let's start with the safe stack first. Let's assume we only use the safe stack. If you branch into unprotected code, we just don't give any guarantees while you're executing unprotected code. As soon as you return to protected code, it continues. So unprotected code is perfectly supported for the safe stack. We don't give any guarantees while you're executing the unprotected code. For code pointer separation or code pointer integrity, it looks a bit different. As long as you don't modify any of the sensitive pointers, you're fine. If you modify the sensitive pointers, then some of the pointers could be out of line. So you're you would miss some of the updates because the shadow location would be written that is not actually used in regular memory, and you would miss the update. So there are no safety guarantees, and you could miss some of the updates. But the unsafe code, if you use segmentation, for example, wouldn't be able to modify the code pointers, even when executing unsafe code.
So which way around is like safer? Like unsafe code loading your safe library, or the other way around?
Well, it just depends, right? While you're executing unsafe code, there are no guarantees. Okay. That's basically how it looks like.
Oh, thanks.
You could run some form of binary instrumentation on top of it to kind of pay a very high overhead for the unsafe code, but it's not what you would want.
All right, we have 3 questions and 5 minutes left, or 4 minutes. Go ahead.
Okay, not exactly a question, just a comment. Casting function pointers to void pointers is not allowed. I don't have the C standard memorized, but I'm pretty sure of that. And ICC and XLC both warn for that, but GCC does not, for whatever reason.
Okay.
I don't know about.
But casting to char and back is allowed.
But POSIX requires it.
Yeah.
POSIX requires it, like DLSIM. You get a void pointer.
All right, thanks. Microphone 2, and then after that, the internet.
C was developed a few years ago, so why?
Say again.
C was developed a few decades ago. So why has it taken so long to find a simple solution?
Well, the solution is not simple, right? It's fairly complex. So we run a whole bunch of type-based analysis. And all these type-based analyses have only come up to speed in the last couple of years. And you've seen, like I talked about C-cured, which was proposed in the early 2000s, I think like 2002 or 2003 or so. And there's been a lot of research going on. And only now we have these frameworks available that we can actually do these heavyweight transformations and then run additional optimization passes on top of it to get the overhead low enough so that it could actually be usable in practice. Also, people assumed that C programmers would write safe code, but apparently it's not like that.
All right, one last question from the internet.
Thank you. I have to read it out. Actually, I have no clue what it's about. In the context of C++, wouldn't all the pointers to instances of classes containing virtual methods be protected, and by extension, all classes containing pointers to those classes as members? Should I read it again?
Yes, please.
in the context of C++, wouldn't all the pointers to instances of classes containing virtual methods be protected, and by extension, all classes containing pointers to those classes as members?
Yeah.
So the answer is yes.
Yeah, the answer is yes.
Okay, thank you.
All right, thank you very much, Matthias Playa.
Thank you.
If there's no more further questions, all right, one last one, really quick. Microphone 3.
I don't know. Is it on? Okay. Expanding on the last question, what's the perf hit on that?
What's the what?
The perf hit, performance.
On which one?
The last question when you get, because that sounds expensive to me.
It actually depends. We only look at the pointers, and luckily, a lot of the stuff is pushed onto the stack. And so we don't pay anything on the stack. We do protect. We do get a performance hit on some of the stuff on the heap. And especially for C++, as was said, we might end up protecting a whole bunch of the pointers with to objects with virtual functions. Depends on the program, how frequent these pointer operations are. There's a full list of individual benchmarks in the paper. Most of the benchmarks are below 5%, some of them are around 10, very few around 20, and the highest overhead we've seen was roughly 80%.
Okay, thank you.
So and for the one with 80%, there's definitely room for future optimization where you can kind of add or reduce the number of checks by streamlining and grouping and reducing the total amount of it.
Thank you.
All right. Thank you very much again, Matthias Playa. This was Code Pointer Integrity.